So that's the main contribution, and let's go into how we obtain it. So the overview is as follows. There's kind of two steps, and one of the steps actually isn't necessary, so maybe there's just one step, but I'll tell you about the two steps. So the first step is we're going to give a correlation intractable family for all log depth circuits. And this will be based on the LWE or even the SIS assumption. So depending on which mode you want here, our construction actually is only based on SIS, which is a potentially weaker assumption than LWE. So that's the first step, to handle log depth circuits. And then we give what's called a generic bootstrapping theorem, which says if you assume an FHE or a leveled FHE scheme with a log depth decryption circuit, then we can get you correlation intractability for arbitrary bounded size circuits. So they don't have to be log depth anymore. They can be any polynomial size and polynomial depth. And this bootstrapping theorem is very much reminiscent of bootstrapping ideas from the fully homomorphic encryption and obfuscation literature. So we do know how to build such leveled FHE from LWE with polynomial factors, and so putting these two things together, we can get correlation intractability for arbitrary bounded size circuits from LWE. But in fact, the first step is really all we need for NISC. So for NIZK, we don't need the bootstrapping because it turns out that the bad challenge functions that we're interested in are already implementable in logarithmic depth. And so step 2 is not really necessary for what we are looking for. So for the rest of the talk, I'll just focus on step 1 here, which is how you get correlation intractability for low depth or log depth circuits. Any questions about this so far? Okay, so just a reminder, this is a repeat from yesterday. It might even be the exact same slide, or pretty close to it. So the SIS and LWE problems of Itai and Regev. So I'll go through this pretty quickly since it should be familiar. We have an integer modulus and dimensions n and m. And the SIS problem is when we are given a uniformly random matrix of these dimensions. You want to find a short non-zero vector z such that az equals 0. And for LWE, the goal is to distinguish a uniformly random matrix A of these dimensions from a matrix which is uniformly random on the top rows, but the bottom row is a random combination of these top rows plus a little bit of error. Okay, so this A prime is uniformly random. It has n-1 rows. And then the bottom row here is S times the top rows plus error. And so just distinguishing between this kind of matrix and a uniformly random matrix of the same size. That's the LWE problem. So as we've talked about yesterday and today, we have theorems which say that if worst case lattice problems are hard, if lattice problems are hard on some instances, then these two problems are hard on the average, right, in the average case. One more tool that we will need, and I think Hotek talked about this yesterday, is this so-called Gadget Function or Gadget matrix. And it works like this. So there's a linear function g. And it's a fixed public function. Everybody knows it. This g can be seen as a linear function from m bit strings, okay, strings of length m, binary strings of length m, to zq to the n. Okay? And if you wish, you can think of g as just being a matrix, and you just multiply g times this m-bit string, and you get out an element of zqn. But there's also a complementary inverse, kind of a one-sided inverse function, which I'll call g inverse. This function is nonlinear, but that's okay. So this function goes back from zqn to m-bit binary strings. And it satisfies this invariant. If you take G inverse of U and apply G to that, you get back U. So it only goes in one direction. We do G of G inverse of U, but not the other way around. We don't do G inverse of G. That doesn't make sense. So this holds for all U in ZQN. Okay, so we'll see why this gadget is very important to our construction in a moment here. Okay. Question? Yes. Okay. Good catch. So I've said here that both the errors are short and the secret S is short. And I think in all our treatment of LWE so far, we have not mentioned that the secret S can also be drawn from the error distribution. So it's short as well, with no loss in security of the problem. Yeah. And I can't remember if we actually need that. I think we will need it, but I'm not sure. Okay, so this is something we can say without loss of generality, but I'm not sure if we really need it today. Leave it as an exercise, exactly. Well, an exercise of whether we need it today, and also an exercise to prove that this is true. Yeah. Okay, so we have SAS with LWE, and we have this gadget and gadget function and its inverse. And what's important is the gadget function is linear. So if you add the two inputs, the two outputs are also added. Okay, so here is our construction on one slide of our correlation intractable hash functions. So the goal here is to get a correlation intractable hash for circuits of size S that operate on L-bit inputs and return M-bit outputs. And M, remember, is going to act as the length of the verifier's challenge. Okay, so we're running a protocol in parallel M times, and so we want to produce an M-bit challenge string. The input here, remember, is the prover's initial message, alpha, which could be very, very long, and so we have really no restriction on that length right now. So here's how it's going to work. We're going to use the techniques that Hotek taught us about yesterday, which is the fully homomorphic encryption and commitment schemes that come from the Gentry-Sahai-Waters and Gorbanov-Fleischmann and Wee works. So our hash key, so the key to our hash function, is just going to be a commitment. It's going to be a fully homomorphic commitment. I'll call that D bar. So the bar indicates that, hat. The hat indicates that this is a commitment to D. And this is just a dummy circuit. This is a circuit from L bits to M bits, and the circuit doesn't have to do anything in particular. It's just some size S circuit that doesn't do anything interesting. Okay, so we commit to such a circuit, and that is the key to our hash function. Why does dummy function? I don't know. It's a mystery. You'll see. Okay. So how do we evaluate the hash? Okay, so to evaluate the hash function, we are given an input alpha, which is an L-bit string. And again, think of this as the prover's initial message, which we're going to hash to obtain the challenge, the verifier's challenge. So the first step is that we take the commitment to the dummy circuit D, and we homomorphically evaluate that committed circuit on the string alpha. So we can take the commitment to D, and using the full homomorphism, we can obtain a commitment to D of alpha. So that's just homomorphic evaluation. So we commit this, or we prepare this commitment, we compute this commitment. The second step is something we call inertify. Okay, we're going to make this commitment here inert. Okay, so inert, I'll explain what that means. But what we're going to do is apply a special procedure which will homomorphically evaluate our special linear function G, our gadget function, on this commitment here. Okay, so what we will end up with is a commitment to G of D of alpha. However, it's a different kind of commitment. It's not going to be a fully homomorphic commitment anymore. It is going to be what we call an inert commitment, Inert means that it doesn't react with anything. So you can't do any further homomorphic operations on this commitment. We're going to squeeze this commitment down to something which no longer supports homomorphism. But it will have another nice property that we will use. Okay, so we end up with a commitment to G of D of alpha, but it's inert, so it has this flat line above it. Okay? And the key property, or one of the key properties of this inert commitment is that it is, the commitment value itself is a vector in ZQN. So this is going to be very important because the commitment C alpha, the commitment itself is in ZQN, but the value that it commits to, G of D of alpha, is also in ZQN. So this is a commitment which has the same size as the value that it commits to. Okay, and that's a rather unusual feature of a commitment scheme. In fact, maybe we shouldn't even call this a commitment at all, but it's an inert something. Okay? It has the same size as the hidden value inside of it. Finally, we are going to, so after having produced this inert commitment, we are going to apply the G inverse function to it to get a bit string out. Okay, so this is kind of not very interesting. We just take the ZQN inert commitment and turn it into a bit string. Okay. So this is what the construction does. This is how you evaluate the hash function. For mysterious reasons, these are the steps that it does. And we'll see why these steps are actually useful. But first I'd like to mention how this relates to the earlier construction of Kennedy et al. And how we avoid the need for circular secure FHE. So the Kennedy et al. Construction has a similar commitment to a dummy circuit. Actually, it's an encryption of a dummy circuit, but essentially there's a hidden dummy circuit in their construction. But it also includes a circularly encrypted secret key. So they have encryptions of a dummy circuit, and then they also have an encryption of a decryption key. And that's where the circular security requirement comes in. We don't have we don't even have a decryption key here. We just have commitments. But in particular, we don't have an encryption of the secret key, and that's how we avoid the need for circular security. Similarly, step one of Kennedy et al.'s construction is essentially the same thing. You just homomorphically apply the dummy circuit to the input alpha, but that's done with ciphertext rather than commitments. Not really a significant difference there. Step two is completely different. So our step two departs completely from the Kennedy et al. Construction, where here we are applying this linear function g, this public linear function g, homomorphically, and we are ending up with an inert commitment. Kennedy et al. Instead apply the decryption function homomorphically, and they still end up with an ordinary FHE ciphertext. So here is where they use the encrypted secret key, and they apply the secret decryption function rather than this public function g. Okay, so that's probably the most significant difference between the two constructions. Okay, so what's the point? The big differences occur here in step two with this inertify and applying the linear function g here. And the key point is that this inert commitment that we compute, this C alpha that we compute here, C alpha is in ZQN and it hides a value from ZQN. And what this is going to do is allow us to compare the commitment and its hidden value directly to each other. These are objects of the same size and type, and we can compare them directly rather than reasoning about what is inside the commitment alone. And that's what Kennedy et al. Do. Okay, so at this point, this is the description of the hash function, the hash family. So any questions about how it proceeds? Of course, I have not said anything about why this is intractable, correlation intractable, or any other security properties, but just to be clear on how this function works. Any question about that? Sorry, I didn't catch all that. Yes, right. So there are some very particular properties of the inert commitment which we will use when proving the security of this construction. One of the main properties of the inert commitment is this, that it's the same size as its hidden value. There will be a couple of other properties that we'll see. Okay, so again, to compute the hash, we do a homomorphic computation of D on alpha. We then inertify that to get a different kind of inert commitment, and then we kind of convert that to a binary string. But steps 1 and 2 are the interesting ones. Good. So let's see why this is correlation intractable. And it turns out that this will follow from the SIS problem. So we don't even really need LWE here, just SIS. So again, recalling that the hash key is a commitment to the dummy circuit. And then this is the evaluation in one line. We apply D of alpha, we apply G, we inertify, and then we get the bit string out of that. So what we have to show is that it is difficult for the cheating prover to find an input h of alpha to find an input alpha such that h of alpha equals c of alpha for any circuit C of bounded size. Right, so let's consider a circuit that has bounded size S, and the circuit maps L bit strings to M bit strings. So imagine, for the purpose of contradiction, that we do have an attacker who manages to, when we give it a hash key, find an input that hashes to C of alpha. Okay. And we will use this attacker to break SIS, to solve the SIS problem. So this attacker, given a commitment to the dummy circuit, manages to find an alpha such that h of alpha equals C of alpha, and this is h of alpha here. So the first thing we should notice is that by the security of the commitment scheme, we can replace the dummy circuit with the circuit C. So the same thing holds, right? If we replace the hash key D hat with C hat, which is a commitment to the circuit C of interest, then the same will hold. The adversary will still be able to do the same thing. So what this means is that, what I've done is I've replaced the hash key from D hat to now be C hat. And so if you evaluate the hash function with this hash key, you end up with this now. And so D has become C here. Okay. So the attacker has managed to find an alpha such that this equation holds. Okay. Now let's do a couple of simple, oh, yes. Go ahead.
Means the simulator knows the circuit C before he gives the hash key.
So the adversary, actually, we can think of the adversary as choosing which circuit it wants to break.
I mean, the simulator knows the C before he gives the hash key to the adversary.
Yes, so the notion of correlation intractability is the attacker declares which circuit C he would like to use. Yeah. Then he receives a hash key and needs to find an input such that the hash of alpha equals C of alpha.
So the adversary should first declare the C.
Can you say that again?
I mean, the adversary should first declare the circuit C before he receives the hash key.
That's correct, yes.
But in the definition of the correlation intractability,
the definition of
the correlation intractability, I mean, in the definition of the security game, the adversary, the adversary is also first declared his circuits, and after that he received the hash key.
Yes.
Okay.
Yeah, that's right. So that's how the correlation intractability game goes. The adversary declares or chooses which circuit C it's interested in. Then it receives a random member of the hash family, and then it is supposed to find an input alpha such that h of alpha equals C of alpha. Good. So, right. So this is the circuit that the adversary has specified that it wants to attack, and then we are going to provide it with a hash key, which is simply a commitment to that circuit that it named. So, and then it will, in some cases, succeed, right? So if it finds an alpha that violates the interactability, then we know that this equation holds. So now we are going to do a couple of easy manipulations to this equation here. So the first thing we'll do is apply the G function to both sides. So if you remember, G of G inverse is identity function. So if we apply G to both sides, then we end up with this inert commitment of G of C alpha is equal to G of C alpha. Right? So we've just applied G to this, which cancels out the G inverse, and we end up with G of C of alpha on the right. And if you remember back, this is our inert commitment C alpha here. Okay, so we have the inert commitment itself equals G of C of alpha. So what we have here is an inert commitment which hides this value, but it is also equal to this value. Right? So the value inside the commitment is also the value of the commitment, which allows, which is what, well, I just said it. Okay, so now it's on the slides. Right? The inert commitment C is exactly equal to the value that is inside of it. And what we will show in the next slide is that this allows us to break SIS. So that is, using our original coins for the commitment C hat, we can derive coins for the inert commitment, and this will allow us to solve SIS. So any commitment, any inert commitment that equals the value it hides allows us to solve SIS. So let's see why that is the case. We'll do that on the next slide. Okay, so again, we have a hash key, which is a commitment to the circuit C. And after evaluation, we have an inert commitment, which equals the value inside of it. And we want to show how that lets us break SIS. So we need a couple of properties of what these commitments actually look like at a relatively high level. So all of the commitments, either inert or fully homomorphic, are all with respect to an SIS matrix A. Right? So we have an SIS matrix A that we're trying to find a short solution for. And there are short coins. So the coins of all the commitments are some short vectors. So they have small norm. And they have this form. So a fully homomorphic commitment to C is just A times some short coins plus some kind of encoding of the circuit C here. So these coins here are a matrix, so they have many columns. Now, as I think Kotek taught you yesterday, when we do the homomorphic evaluation on C hat, there is a corresponding manipulation of the random coins that occurs. So if you do this homomorphic evaluation, transforming C hat to C alpha hat, then there is a corresponding transformation that applies to the coins inside the commitment to get some other coins R as well. So if you know this alone, you can compute this. But if you know this and the coins, then you can compute both this and the resulting coins inside the derived commitment. So that's what we do. We say we kind of recompute this. We take C hat to C alpha hat, and we see how the coins evolve. And similarly, there's an encoding of the value C alpha here. So that's step one. The next step has to do with the inertify. When we do the inertification, when we convert to an inert commitment, a similar thing happens. Converting from here to here, okay, the C alpha, there's a corresponding thing that happens to the coins of our commitment here, and they get, there's a corresponding computation that occurs on the coins to get a vector R as the coins of the inert commitment. So someone who knows the original coins can do all these transformations to get the resulting coins of the inert commitment. Now let's remember what we knew about the inert commitment. So the inert commitment has the following form. It's A times some short coins in a vector of short coins, plus G of C of alpha. Okay, so that's the form that an inert commitment has. But remember, what did the inert commitment itself equal? Okay, what do we know about the inert commitment? We know at height it's G of C alpha, but what is the commitment itself equal to? Just to make sure you're still with me. Right. The inert commitment itself is also equal to G of C of alpha, right? That's what we have up here. So GC of alpha is equal to the inert commitment. So let's fill that in. Right. So what we have here is the inert commitment itself, which is A times coins plus GC alpha, is itself GC alpha. Now, pop quiz, okay. Exercise for the audience. How does this solve SIS? Okay, I claim that this lets us solve SIS. Thanks. I think someone said it. You do? R alpha. Okay, R sub alpha is our solution. How did you get that? Yes, okay, good. So let's just subtract this value from both sides. Okay. Then we are left with A times R alpha equals 0. And that's exactly what we want, right? So the goal is to find some short vector such that A times that short vector equals 0, and that's what we get. So what this tells us is that A times R alpha equals 0, and that indeed is a solution to SIS. So to recap this argument briefly is we start by providing a fully homomorphic commitment to our circuit. We provide that to the attacker. The attacker then gives us an alpha for which C alpha equals G of C of alpha. And we know that inside of C alpha is as well G of C of alpha. So the attacker gives us this alpha, and then we basically reevaluate the hash function. We evaluate the hash function on that alpha, but we do so also keeping track of how the randomness evolves during those homomorphic operations. Okay? So in step 1, we transform this randomness into this randomness, these random coins, for the homomorphic commitment to C alpha. And then we do the final inertify step, which also transforms these coins into these coins. And now we know that this holds, and so these coins here are a desired solution to SIS for the matrix A. And so that's how we obtain an SIS solution. Any question about this so far? Oh, and by the way, I've lied about one important, well, I won't call it minor. I've lied about one important thing here, or at least I've left it, I've left a minor thing unspecified here. There's one thing missing from this argument. See if you can find it.
How can we make sure that the coins are short?
How can we be sure that the coins are short? Is that the question? Yes, okay. So the original coins are short by construction. And what Hotek showed yesterday is that the coins evolve where they remain relatively short. So there is some increase in how long they become in their norm, but when you go through these homomorphic evaluations, the coins do not grow by too much. So we can bound how large they grow, and ultimately we end up with these coins of the inert commitment, which are not too much larger, and so that gives us an SIS solution with a certain length to it. Yeah, that's a very important part of the argument for sure. Okay. So what did I leave out? Anybody have an idea? It's at the very end. Does this really solve SIS? If A times R alpha equals 0, does it really solve SIS? Well, to solve SIS, you need a short solution, which this is, but it has to be non-zero, yes. And as I've written this, there's no real guarantee that the vector R alpha is non-zero, but there's a very easy trick you can do to guarantee that. So I won't explain that, but it's a simple exercise. All right. Or you can, I guess you can solve ISIS as well. That's another way to do it. Okay. So any further question on this argument? So what we have to do now, what remains to show is, so this step to this step is already handled by what Hotek told us yesterday, but this step to this step is new, and so I have to show you how to do the inertification and how the coins evolve when you do the inertification. There we go. Okay, so let me tell you how the inertify works, and then basically the construction and proof will be complete. So inertify, what inertify does is it allows us to convert a fully homomorphic commitment to an inert commitment, and in the process it also applies any linear function you want. In this case we use the linear function g, but it applies any linear function you want to the committed value. And so we start with a commitment to a string, and we end up with a commitment to g of that string. So we are given this commitment x hat, this fully homomorphic commitment to x, and then we may or may not have the corresponding coins for it. And that commitment has this form. So it's A times some short matrix plus the individual bits of x times this gadget matrix G. So this is the form of the fully homomorphic commitment or ciphertext from Hotek's talk yesterday. And our goal is to compute an inert commitment of L of x and the corresponding coins for some linear function L. Right? So it can be any linear function, it turns out. Right? And the resulting form of this, so the inert commitment to L of x should have the form A times a short vector plus L of x. And so importantly, there is no gadget here, there's no nothing, right? This L of x is just a vector, and we have A times R plus that vector. So that's the form that we desire at the end. So let's see how to convert this part above to this part below. Okay. So what we can do is simply write this linear function, L of x, as the sum of xi times ci for some fixed vector ci. Okay, so it's a linear function, so it always has this kind of representation. So in particular, you can just evaluate L on all the standard basis vectors, right? Vectors which have a 1 in a single position and 0 everywhere else. So that tells you what these CIs are. Okay, so L has this form, and now what we'll do is define one very tall but low norm vector, which is just the G inverse of all these vectors CI. Okay, so we just stack them on top of each other. And that gives you a binary vector of very large dimension, m squared. Good, so let's just verify how this is going to work. we will take our fully homomorphic commitment to X, which is this big wide matrix, and we will multiply on the right by this binary vector VL. And magically, this just kind of works out as you want it to. So let's do the substitution. If we take plug in X hat, take this as substitution, then you end up with first the A times R part. A times R gets multiplied by VL, and overall this is just a short vector. Right? We have a short matrix times a short vector. That's going to result in a pretty short vector. Okay, so we have A times the short vector. Now let's look what happens over here. We have this big block of matrices, and they get multiplied by this vector here on the right. And so what happens is the G and the G inverse cancel out, and you're left with x1 times c1, and x2 times c2, and xm times cm, like so. Right? So you basically end up with this form of thing, and now we have A times a short vector, and what's left over is L of x here. And that's it. So we have, we take the fully homomorphic cipher commitment, that is, multiply it on the right by the special vector VL, we end up with a commitment that has this form, and if you know the original coins, you know the derived coins as well. And that is the inert commitment to L of x. So rather simple transformation, flattens the whole thing down, gives us our inert commitment, which we know the coins to, and those coins will act as a SIS solution. Any question about this? So that is the construction based on SIS, and I just want to mention briefly in one slide what the Lwt based construction looks like. This is computationally a little bit over time. Okay, I think I'll skip this. I'll just put this up here in case you're interested. You can take a picture based on time. But it's simple. We're just going to replace the hash key with a homomorphic encryption, and with some similar argumentation, we can show that there does not even exist an input that hashes to C of alpha. So that's quite cute. It just kind of works out in a very similar way. Okay. So I'll also skip this here. We have some ongoing work which handles the radical inefficiency of this NIZK. So it's extremely inefficient. It's a very large polynomial runtime on top of also going through the Cook-Levin reduction and all kinds of overhead. So there's a different approach which will work with a much cheaper bad challenge function and can operate directly on a verification circuit of a desired shape. So I'll finish up with just mentioning a couple interesting open problems here. So one thing would be, we managed to get correlation and tractability for log depth circuits from SIS, but it would be nice to get it for more than log depth circuits. So as soon as we leave the realm of log depth circuits, we have to introduce LWE, or that's what we currently know how to do, through the bootstrapping transformation. And if you don't want to have LWE, then it would be nice to have a construction which doesn't involve it. And we can do it with super polynomial factors, but to do it with polynomial factors is the open question. Another nice question is, there's a relaxation of NIZK, which is called non-interactive witness indistinguishability, which has its own advantages. For example, you don't need any setup. You don't need any, you don't necessarily need any common random string or any common reference string. And so to be able to do that from lattices would be very nice. It's interesting that Groth, Ostrovsky, Sahai kind of get this for free from their NIZK system, but they need a combination of properties which we do not have. And so it's not clear how to use their argument. A different argument seems to be needed. And lastly, this is probably a very hard question, but a really important one, is we get correlation and tractability for bounded size circuits, and the size of the hash key grows with the size of the circuits. And so what would be nice is to have a hash key which is a fixed size for any size circuit of correlation and tractability. We know how to do this using obfuscation or similar very heavyweight techniques, but we don't know how to do it from LWE. And finally, this is a very tough question to get succinct zero-knowledge arguments. So that is where the proof size is very small. That's the kind of thing that people like to put on a blockchain, right? They want a very succinct proof and fast to verify, but our current proofs are very large and slow to verify. So could that be done with LWE or through the Fiat-Shamir methodology? Okay, so I'll leave you with that. Thank you, and we can have lunch.
Okay, I think we only have time for one question.
Excuse me, I learned that in your paper you build two different CIH, one for circuits and another for branch program. I wonder what the difference between them. In other words, I want to know more details about the branch program. Okay.
Yes, so the question is, we assumed that we had fully homomorphic commitments for circuits, but if you wish, you can use the fact that the GSW scheme is fully homomorphic for branching programs as well, and limit your attention to branching programs. So I think you would just get correlation and tractability for whatever class of branching programs that you can evaluate homomorphically here. But everything goes through in the same way. So we know that branching programs can implement log depth circuits, but there are other forms of branching programs you might be interested in as well. So basically, you just need your FHE to be capable of computing that kind of branching program.
Okay, let's thank Chris again for the great talk.